So welcome everyone to the fifth problem solving session. You all can hear me, right? Can one of you just confirm? If you can hear my voice and see my screen, if you can hear my voice and see my screen, can you just give a brief thumbs up? Oh, thanks. So we'll wait for another minute and then we'll start. So before getting into the content of week 5, I would like to clarify one of the question I discussed in last session, that's regarding the log likelihood ratios that is being fed to soft decoder. So there is a misunderstanding from my end. Like for example, if it's BPSK, like whether you are transmitting 0 or 1, then okay, you have part symbol only one LLR ratio, right, for 0 and 1. But the issue is when I move to higher modulation scheme, for example, QAM, I have 2 bits per symbol, or 16 QAM, uh, where I have 4 bits per symbol. So basically, each symbol in that scenario, let me write it down here. For example, BPSK, I have only two options, 0 and 1. So each symbol produces one log likelihood ratio, that is basically the ratio between 0 and 1. But when it comes to, let's say, QPSK, we have four options, right? 0 0, 0 1, 1 0 and 1 1. In that scenario, each symbol carries 2 bits, so each symbol, last time I mentioned it produces one LLR. It's not true, it produces two LLR actually, corresponds to this in phase and quadrature bits. And basically the idea is that if I move even higher in the modulation scheme, for example 16 squam, like my modulation order, if I call it M, so basically each symbol is going to produce log base 2 M LLR values based on the bits, and those are being fed to the LDVC decoder, which sorry, the soft decoder, and then it performs the rest of the calculation. So let us get into the content of today's, which is mostly around the control information. So before getting into answering the questions, can you just briefly tell me what is the fundamental difference between the uh, transmission of data or data payload and transmission of control channel? So what is the uh, primary difference between them when I talk about the data payload and the downlink control information that we called DCI? So those are eventually bit sequences, right? So what are the main difference between them? And by the way, I'm not talking about the transmitter and processing chain, the receiver process chain as of now. I'm just talking the very fundamental thing, like when you talk about the data payload and the downlink control information. Both are sent from the MAC layer to the physical layer. So what is the main difference between them?
The number of bits are very less as compared to, the data shared channel or data that is transmitted. Number
Correct.
of bits are restricted. That is the first thing.
Absolutely correct. So
And the
there are
second thing is DCI. So they transmitted an symbols in the slot. So maybe first few symbols in the slot mostly.
okay, okay, absolutely correct. So first thing we observe is where in terms of data payload we are talking about thousands of bits or even lakhs of bits, and now when you talk about control information, suddenly the order of magnitude is way less, like order of tens or something like that. So this is a good point to ask you just another question related to this, like which one is more crucial you think, like the data or the control information?
Most crucial is control
Control
information,
information,
because
and
that is
why?
going to decode where the data is coming, when in which symbol the data is at. I mean, from which symbol up to what length data is present in the OFDM slot.
Okay, so basically you are saying if some error happens while recording the control information, the rest that is follows, like my data decoding will be like completely in mess, right?
Yes, true.
Okay, so what are the methods we take to protect this so precious control information of ours? I guess if it's that much crucial, so we have some additional layer of protections, right? So what are those methods usually specified in the standard?
Especially polar coding. Polar coding is used.
True, you use polar coding, fine. And what on top of that, like something else we do?
CRC plus polar coding, both are used.
Okay, so is it possible for like for control information, can we go for very high modulation scheme even if my SNR is very good?
No, QPSK, most reliable QPSK is used.
Okay, so no matter what SNR we have, we should always go with QPSK, right? So that's what you are saying. Okay, so we go for QEM or QPSK, and we go for CRC and polar coding, fine. And by the way, why exactly we are having LDPC encoder and decoder in context of data payload, but now we are going for polar? Why is that exactly?
This performance of LDPC for lower, frame size or packet size is not that good as compared to polar coding.
So you are saying it's going to produce high block error rate,
Correct,
like
correct,
it's good for large size blocks like
correct.
4000 or above, but
Yes,
when you are talking about
yes.
in tens of bits, it's not
Hmm.
good. So polar we are going
Hmm.
to use. Okay, and
Correct.
any other benefit of polar coding?
The power consumption seems to be
Okay, the
under control.
power
Yeah,
consumption and this hardware implementation is quite less
yeah.
complex, and of course power consumption is lower. And how does this power consumption lower exactly helps? Because like when you compare with the LDPC decoding thing.
Yeah, so multiple times it has to check for DCI, where the DCI is coming, in which slot. So blind decoding has to happen.
Okay, but for when I talk about LDPC encoder decoder, it need to run only once, or it has to be blind also.
It has to run only once. It knows in which slot, in which symbol in the slot, the data is there.
Okay, Okay, so it basically knows where we exactly know in which resource block to look for our data. So we'll run it once, but when it comes to control information, we don't have any knowledge, like prior
True, true,
knowledge.
true.
Like we have some initial knowledge, but that is not enough, right? So
Yes, yes, yes.
fine. So let us try to answer this thing here. First of all, here it's mentioned DCI format 10. So there must be a DCI format 00. So what does that denote? It's mentioned DCI format 10 here. So let me ask you here, like, is that for uplink grant, or is it for downlink assignment? When I talk about DCI format 10,
Downlink assignment.
downlink assignment, and if had it been for uplink grant, which one should we use?
01.
Fine. Then how should I calculate the number of DCI bits here, the length of DCI bit? I have these many fields, these 6 field here. So let's start with the simplest one, identifier for the DCI format. So how many types of DCI are possible?
Two types.
Two types. So basically I need only one bit to distinguish between them, either 0 and 1, right? So one bit, fine. What about this one, second one? New data indicator. What are the possible chances here, that is it a new data or not a new data? So how many possibilities? So
Two
whatever, two
possibilities.
possibilities. So either it's a
Two
new,
possibility here.
yeah, so
Yeah.
it's either new data or it's not. So how many bits I need to specify the choice?
One bit.
One bit here also. Then comes HARQ process number, which is not discussed in the
Four,
you are answering something, can you just repeat once?
four bits.
True, for 5G NR there are 15, sorry, 16 process IDs. 16 process IDs, HARQ process IDs. So that means I need 4 bits. And what about this one? Physical uplink control channel resource indicator.
Three bits.
3 bits. These are basically specified in the standard. What about to point the redundancy version? How many possible are there?
RV only two bits are possible.
Okay, and why I need only 2 bits here? Like basically I am asking.
RV0 to RV0 to RV4. RV3, sorry.
Okay, so
Three.
there are 4 possible
Four
RVs,
possible.
so therefore 2 bit, fine. And what about modulation and coding scheme?
MCS 27, so I think 5 bits.
MCS 27. So MCS 0 to MCS
Yeah.
27, right? So in total
Yeah. Yes.
28. So nearest factor
Yeah.
of
So
2 is 32, that is 5 bits. So in total, what should be my length here? If I sum all them up, 1 here, another 2, 4 plus 2 6, plus 3 9, plus 2 11, plus 5 16 here. So we'll have 16 bits. By the way, what is the maximum possible length for DCI in downlink? Maximum possible length of DCI in so what is the number here?
Is it 140?
140 bits. 140 bits. Okay. And we know that DCI is also transmitted to inform the like DCI is for user and okay, we'll come to that later maybe. So next we'll see what change happens in the transmit chain here for PDCCH. So as of now you're fine that our DCI is coming from MAC layer, good enough. So what the next thing should happen?
I think CRC. Adding CRC.
CRC, fine. And what we do next?
Scrambler.
Scrambling.
CRC scrambler.
CRC scrambler. Was that block present while considering PDSCH chain?
No. No.
It was
No.
not there. Okay. So what does exactly happen in the CRC scrambling stage?
This RNTI is used to scramble the CRC.
RNC. Okay, let's talk about
Last
the.
six, last six, last 16 bits are scrambled.
Okay, so let's say I have A length DCI. Now after passing through CRC, we'll have A plus the CRC append block output. L is the number of CRC bits, 24 here. Then I've got a sequence. Then what you are saying that I need to scramble with something called as RNTI.
Yes. Yes.
Scrambling with RNTI. And how many bits is this for RNTI?
16 bits.
16 bits. So if I use a 24-bit CRC and I scramble with 16-bit RNTI, does my
Prefix. The first 8 bits are retained as it is, and then last 16 bits are scrambled.
okay, so does the control information gets impacted by scrambling?
No. Control information is as it is.
It doesn't, right? So
age as it is.
Even the first 8 bits of CRC is also not
COC,
affected, right?
not a
Only
yes,
the
true,
last
true.
16 ones. And
Yes,
this RNTI, uh, what does it specify?
it is cell dependent. For every user, it is a unique number that has been assigned by base station or G node B.
Okay, fine. So after scrambling, what is being done?
In CRC interleaving, I think, and then polar coding, encoding, which was not discussed still in the class in this week. CRC interleaving, and then polar encoder,
CRC interleaving, then comes
polar polar encoder,
and then comes
and
something
I think
called,
there is one more block. Yeah,
there is another something called sub block interleaver,
so, correct.
which will be discussed in the week
Both
6, I guess.
both are I think not discussed. CRC interleave and sublock interleave both are not discussed in
Okay,
this week.
CRC interleaver is discussed to some extent. We'll actually see a problem based on that. So let's see.
Okay.
Uh, okay, you have done CRC scrambling here, fine. And was this CRC interleaver kind of thing block present in the PDSCH scenario, or was it not?
Yeah, everything is interleaved. It's interleaved in SCH is there. It's not only CRC, every entire block is interleaved.
Okay, okay, fine. So you're talking about something called blind decoding. So what is the idea behind that? Like why we need to go for it? Okay, first let us start with what the most common information this DCI contains. What are the like most common things for a
The
particular user?
where the data is, from which symbol it starts, what is the length of the data that is present.
Okay, so MCS index, the number of resource blocks, that's what you are saying, right? Okay. So in the first question that we answered, there are 6 fields, right? Can you but this is a simplified scenario. Do you point out few fields that you consider missing in the sense those are not given here, maybe to reduce the complexity, but they might come. For example, that MCS part is there, okay, but where should I look for the resource allocation thing, where it falls in the time frequency grid? Just in context of this question here. So what I can see here, there is
So
no mention in the time domain and frequency domain allocation. Both are kind of missing in the sense, I'm not saying they forgot to something, they just keep things simple here.
they're not in the question. They are not in the
Yeah,
question.
they're
Yeah.
not in the question. So let us so basically when you saying that I need to know where the data is coming, I need to know the time domain allocation and also frequency domain allocation.
Yeah.
So basically, if time domain allocation, we are talking about symbols, right?
Yes.
And for frequency domain allocation, we are talking about PRBs in terms of PRBs. Fine.
Yeah.
So let us first talk about time domain allocation. So what information does it carry?
From which symbol S0 and I think L, length of the, in how many consecutive symbols the data is present.
Okay, okay, that's correct, absolutely correct. But is there something called as offset?
Yeah, S0 offset. Start from where it is starting.
Okay, so what
With
does it?
respect to relative to DCI slot. Relative to DCI symbol.
Okay, okay. So what does it offset denotes?
S0, I think.
uh,
Yes,
okay,
notation.
uh,
The number offset from the current symbol. How much offset is from how much offset the data is starting.
okay, let me then try to draw a slot here. Let's say DCI is coming somewhere here. This is DCI, and then this I am talking about nth slot, and then I have this n plus 2th slot. This is the th symbol, and this is consecutive L symbols. So what are the key informations here? Like three key information I can infer. uh, First of all, this offset we are talking about, is that with respect to symbols or something else?
With respect to DCI, offset is there. Where is the symbol?
Yeah, true, with respect to DCI. And we, when we call this offset, we actually call it slot offset. For example,
Yes.
if my DCI is coming at nth slot and it is carrying information that my data is going to be n
Hmm.
plus 2th slot, then my slot offset is going to be 2 here. So that's one thing.
Oh yeah.
So user know that
Hmm.
exactly which offset to look into, which received its uh, DCI in nth slot, and if it gets the information that okay, slot offset is 2, then it's already know that I need to look at n plus 2th slot. And then comes this information, the sh symbol. So that is the starting position. That is the second key information, which mentions at which position user should start looking for data. And then comes the number L here, and that is number of consecutive symbols. So if I am carrying information, let's say basically my slot offset is 3 and my, okay, let me write it down here. So if let's say I am giving information like this, slot offset 3 S5 L4. So how should I interpret this information in terms of uh, symbol level allocation? Let's say user receive this particular information, so what it should infer from that?
So in the third slot from the where the DCI is present,
Yes, true.
so 1, 2, 3, yeah, and then the in the symbol starting from symbol number 5 in that slot, and four such symbols are there, consecutive symbols.
Okay, so it exactly knows where its data is coming, right? So this
Yes.
time domain allocation, so how many bits we need to uh, tell the user where it should be looking for? Of course, we cannot send these numbers like that. There are certain
Yeah.
combinations. So how
Yes.
many such
Yes.
combination possible for, let's say, if I consider offset 0? Actually in the course it's, yeah,
Yeah.
yeah,
Of
you are
course.
saying.
Yes. Yes. For offset 0 and the S could be from 1 to 11.
True, actually
Uh,
first one or
the
two,
DCI is in symbol 0
yes,
mostly.
true. So there are 16 such possible combination for offset 0, so that means you will have 4 bits. And okay, this is a good point, like if we forget about this offset thing, let's consider it's fixed kind of, whatever be number it is there any
Hmm.
restriction on S and L, like can I pick any arbitrary combination here?
No, no. L should not cross this slot boundary. L
L
should be
should not.
within that.
So let's say if I choose S something as 10 and L as 7,
Hmm.
so that is the invalid
No,
combination,
that
right?
that is invalid. Yes, 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 yes.
Okay. And when I talk about the downlink, can this slot offset it has a upper bound, like some restriction, or it can
Yes,
go?
it has upper bound. Slot offset also has upper bound.
So in downlink, what is the upper bound here?
I think
0 to
three
3.
or like 0 to 3. Yeah, three upper bound is 3.
Downlink, okay, downlink in upper bound is 3. And what about uplink? If I talk about uplink grant, that information should come here only, right? Because base station is going to inform user where to transmit. So in that case also slot offset can be 3, or it's like I'm asking whether it's less or more in case of uplink. Actually, when it comes to uplink, you have a kind of higher threshold. You can have slot offset up to 7, 0 to 7. Whereas in downlink, it's limited 0 to 3. But in uplink, it's 0 to 7. Okay, this is. Can one of you point out that why we exactly need the CRC scrambling thing? CRC I understand, okay, it has some common agenda, fine, but why this CRC scrambling exactly is doing here?
So it can identify whether this DCI is relevant to that UV or not.
So does the base station explicitly tell user that okay, this
Yes.
is going to be your DCI,
No,
or
no, not explicitly.
not
After
explicitly?
unscrambling, it can detain. After unscrambling, the CRC is valid. It knows that the DCI is for itself.
So you are saying that CRC scrambling is the base station's way to inform user that it's the
Correct.
DHC of yours,
DCI for that user.
DCI for yours.
Yes.
Okay, okay. So in that context, what should be the answer for this question here? That possible slot offset.
Obviously. 3. Obviously.
Uh,
3.
it's actually uplink shared channel. So
Uplink 7. 7 there.
7 then, right?
7. Yeah.
Actually, if the question asks that possible slot offset, it can be all of them, right? 1, 3, 5, 7.
Achha. Max, not max. Yeah.
If I talk about the possible. So 7 is the
Yeah.
maximum,
Yeah.
but
Yeah.
if I talk about the possible, it
Yeah.
can be all of them.
Yes. Yes.
So about this one, so what should be the DCI type that contains resource information related to physical uplink shared channel?
Format 01.
Yeah, so it's both actually format 01 and format 00, whereas format 10 and format 11 for PDSCH. Okay, here comes this question. So what is the maximum number of blind decoding attempts can be made by user for DCI detection in a 5G NR with 60 kHz subcarrier spacing?
20.
20. Okay, actually no, you are close to answer, but no.
This, 20 is for, I think, 120 kilohertz subcarrier
Okay,
spacing.
let me write it down here. Correct, for 120 kilohertz subcarrier spacing you have 20
And for 30, he has said 36.
decoding attempts.
For 30 kilohertz, yeah, for 30 kilohertz, 36 attempts.
For 30 you have maximum 36 possible. Fine.
And for 60 watt.
For 60 it's actually 22.
It's 22.
Yes, 22, and for 15 it's 44. So in this assignment questions can be any of the subcarrier spacing, so you'll have these four, so you'll have your answer based on that. So it's mentioned that maximum number of blind decoding attempts. So does it necessary that when I talk about blind decoding, that every time I have to decode the entire control payload and then only I can decide that it is not meant for me, or there is some uh, let's say easier way or shortcut to reduce that pain of blind decoding thing?
Yes, early termination can be given. Yeah, that's why CRC interleaving is there. Early termination.
Okay, so this blind decoding thing, like what is the issue like we are going to encounter, like what are the problems with that?
Once again, power consumption issues, battery drain issue. To avoid that.
Power consumption issues, right? So as of now we have not mentioned anything about where should DCI appear or something. So if I talk about the time frequency grid, let's we talk about one slot corresponds to 30 kilohertz of subcarrier spacing. So that means my slot duration is 0.5 millisecond, right? And in that 0.5 millisecond I have, if I consider a standard 100 megahertz bandwidth, I have 275 PRBs and 14 symbols, and DCI can appear anywhere in that, right? So essentially as a user, do I need to look into all this 275 times 14 places to look for a DSI every zero point 0.5 millisecond, or is there some smart way standardization has defined that okay you can only look at these certain places like that? Because this maximum number of decoding attempts, I see this is clearly much less than the possible combinations. Like if I talk about 275 cross 14, that many places I can look into in one slot. So is there anything like can okay, first of all, can DCI appear anywhere in the slot as per standards?
It should be in first three symbols.
Okay, okay, so I think yeah, so the more okay, by the way, like is there any specific name they are being called, like where the DCI can appear?
It's called duration.
Code
uh,
set.
Code set, correct. So code set stands for
Control resource set.
Control resource set. So they have some fixed places in that time frequency grid corresponds to one slot, right? We'll see about code set later in much more details. So if I talk about a very common scenario, where are these code sets usually should appear, as you already mentioned, at within first three symbols, right? So can you tell me about one exception where can happens when code set maybe appear somewhere in the middle of the slot or something? Is that possible for some exceptional scenario?
Yeah, for URLLC it can.
Yes, it is possible.
Okay.
URLs
And why these exceptions is required?
to reduce the latency.
Okay, so basically you are saying that for URLC user there is strict latency requirement, so it cannot wait for the entire slot duration. So for them exceptions can be made, code set can be sent
Yes.
in the middle of a slot or later. Okay, fine. So about this polar encoding, so what is the intuition behind that, like polar encoding? How does it really work? You did your CRC append, fine. You did CRC scrambling, let's say, and you have done CRC interleaver also, good enough. Now you are feeding to that polar encoder, right? So what does it exactly do? I'm not asking like in terms of math really, like what is the design principle, or how we can explain it in easy words?
So it creates multiple virtual channels, n virtual channels, and the data is sent in the most reliable channel. Actual message bits are sent on over the most reliable channels.
Okay, so you create some n virtual channels, fine. And now this n can be any number, or is there some restriction on this n here?
I think the code rate is should be less than 1 by 8. So there is a restriction. Code rate should be greater than 1 by 8, I think.
Okay, let us write it down here. So if we talk about polar encoding, a few information saying that there are n virtual channels, and message bits are transmitted over the most reliable ones. I have also mentioned that code rate should be
Greater than 1 by 8.
greater than 1 by 8. Like in context of PDSCH, is there any uh, mother code rate here, or there is no concept of mother code rate in case of polar encoding?
There is a, yeah, go ahead.
So
There is a
you
rate matching block, no doubt. Yeah, there is a rate matching block afterwards.
okay? So like what is the mother code rate for polar encoder? Mother code
I
rate
think there
is
is no mother code right here.
okay, but if I don't have any mother code rate, then I will have the rate user is going to ask can keep on varying, right? So I need to have separate sets of polar encoder decoder for each of those rates. That was the idea we have got from LDPC encoder decoder, right? So mother coded
Yes, yes,
here
yes.
is 1 over 8. Then you will have rate matching that you can do on top of that, no issues. So about this n virtual channels you mentioned, fine. So is there any restriction on this number n here?
It's power of 2.
Power of 2, that is one restriction, fine. And anything else? Like some upper and lower bounds in context of polar encoder?
Yes, and min and max is there.
Okay, let me check once.
They are separate for lower bound and upper bound.
Yeah, for downlink, Nmax should be 512, and for uplink, it is 1024.
Okay, so if we talk about downlink here, Nmax is 512 and uplink Nmax is 1024. Fine. So is there any what is that lower threshold like a minimum of something?
32.
32. Okay, so in downlink, what is the DCI length possible? If I talk about the DCI length is A, you have mentioned already its maximum is 140 bits. Is there any lower threshold also?
12.
12, okay. But let's say whatever DCI I am transmitting has a length of just 5. So what should I do in that scenario?
Then padding with zeros.
Okay, so I should pad with 0 so that it comes to
12.
12. Okay. And when I append CRC on top of that, what does this length become?
Plus 24 on both sides.
So here I have
36 to
36,
164.
64. So let's come back to the idea of polar encoding here. We are creating n virtual channels. Message bits are transmitted over the most reliable ones. And what is the math expression here, by the way? The polar encoder.
Just message vector into matrix n matrix. Message vector, the row vector into matrix.
So I have some message vector you are saying and some G here, which is
Matrix,
on
yes.
matrix. So it is a transformation matrix similar to this parity check matrix appear in case of LDPC encoder. Fine. So what is this U here, by the way? This U here, what is its length? Is that let's talk about this A plus CRCS K here total. So this U here is size K or size N?
Size n.
Size N. Okay, but I only have K bits, right? So how do I fit this K bit DCI plus CRC into some 1 cross N vector? How do I do that? So I have some this a plus crc, let's say some k bits, and that I need to fit into some uh, greater value, that is n cross 1, or in this case 1 cross n. So how do I choose that? Like of course u has a greater length compared to k, so how do I fit it there?
Divide it into two sets. One is information set and another one is frozen set. To the information set, fill those k bits, and actually, I didn't get this point where Sir is explaining completely. Uh,
Okay, so which part you are saying? Like so let's say we have,
yeah, like
okay, let's write what you are saying as of now. So let's say you have total of n elements, right? If I look at the structure of u, that is u1, u2 up to un, but I have now only k bits where k is less than n. So the question is like where to fit those k bits. So and how do you make the choice, by the way, about the information set and the frozen set? That's based on the reliability pattern, right? I mean, you have already, as you mentioned, you have n virtualized channels where some of them are good and some of them are bad, and what does it depends on really, these like channels being good and bad?
It depends on noise level.
Depend on your channel condition and your
Yeah.
code length also, right? Or
Mostly channel condition only.
yeah. So fine, so let's say you are fitting those k information bits into the best k out of n channels, and what is the logic behind that, like why we are doing that, like basically why we are trying to send these k bits over the best channels?
Obviously, to minimize error,
So their corruption is
to
minimized.
recover the bits, to recover the bits, message bits
Okay,
reliably.
okay. So all these things you are doing so that your bits, the probability your bits getting flipped is least, the chance.
Yes.
So when you talk about the vector u, we have capital N indices. We are now dividing them based on information set and the frozen set based on the channel conditions here, and putting these k bits in the information set. And what we do about this frozen set index, by the way, if let's say I is in frozen set, what I should set u of I to?
Then 0.
0. We set them to 0. Fine. And is there any segmentation happening here, like DCI need to be segmented or something of that sort?
yeah, for uplink, we'll segment, no, but not for downlink.
Okay, downlink we need not segment. And why we need not segment for downlink?
Like DCI bits are very less compared to uplink.
So uplink you have nmax as 1024, right? And what is the possible DCI length for uplink? 1706, right? So that's clearly more than
Yes.
your nmax. So that is why you need to
Mm.
go for segmentation in that scenario. But here we don't need it.
Sir, I have a question. Like here, we have just K information bits, right? That is A plus CRC.
Yes.
So how are we converting that to N bits? Is it like you said, like from the U, we are grouping that U into two sets. One is information and another one is frozen.
Yes.
And information, whatever we have grouped, that contains those K bits only.
Yes.
And whatever that is in frozen, it is completely zero.
Yes.
So is it like out of N bits, K bits are from information and the remaining are all zero?
Yeah. So it's something of this sort. Let's try with example where let's say we have k is equal to 3 bits and u, let's say the n is 8. Okay. So u is this is u1, u2, u3, u4, u5, u6, u7, u8. Now you, based on the reliability pattern, you find that the channel corresponds to the second bit here, fourth here, and fifth here are the most reliable ones. So you have here your k1, k2, k3. So you are putting k1 here, k2 here, k3 here, and you set u1, u3, u6, u7, u8 as 0. So that is how
Okay.
you are creating the vector u here.
Okay, sir, I got it.
Okay.
Uh, can I ask a question?
Yeah, yeah, sure.
How will you know the most reliable channels?
How do I know the best channels?
Yeah.
Okay. That's the mechanism I don't really know. I mean, you can find it based on the reliability pattern, but I haven't studied polar code in that depth. I just know the terms only. But only thing I know, like what polar code does is like it kind of polarizes the channel in the sense it either becomes good or bad at a particular bit level. And how does it happen? I don't know. For that, I need to study also.
Okay. Okay.
No, the professor said that for fixed value of n, there are many ways to find out, I mean, these patterns. There are
Yes, yes,
ways to find out these patterns here.
yes.
That's what professor said. Only that, I mean, line sentence he has spoken.
Okay,
There are ways to, and because it's a proprietary code, no, polar code, so that's why
okay, okay. So you are
there can
saying
be
that
issues. Yeah,
under.
revealing information. Yeah,
Okay, so you are
for
saying.
fixed n, there are many ways to find out. Yeah,
Okay, so you are saying since it's proprietary, the underlying mechanism is not exactly revealed, or
Hmm. Yeah, yes.
okay,
But I mean, there could be papers available to know it. But this, he said, it's a proprietary code. Polar
okay,
code is a proprietary one. Yeah.
okay, okay. Thanks for the info. So we have a CRC bit sequence here of length. How many? Let me check. 4, 8, 12, 8, 12, 16, 20 24. Okay, so 24 length CRC bit sequence, and the RNTI is value as given as 21400. So how am I supposed to find the scrambled CRC bit? What should I do first?
Convert the RNTI to binary and then do XOR operation.
So I need to have this binary equivalent of this. Binary equivalent. So 2 to the power 10 is 1024, and 2 to the power 15 is, let me calculate once.
2 raised to 15 is 32768.
Okay, 32768, and this is 21400. So how am I supposed to find the binary equivalent of this one here? It's a 16-bit RNTI. The first one is of course going to be 0 only, because it's, as you mentioned, it's 32768. Second one is of course going to be 1. Zero here. So do we have 16 bits here? 4, 8, 12. Okay.
Sir, in the quiz question also, there was a different RNTI value that was also coming 15-bit binary value.
Okay.
That's fine there. So it is 10, 100, 111, 0011000.
I'm also getting what Prashant is saying.
Yeah. So it is. I have used ChatGPT.
Divide by 2, then storing the remainder.
Yeah, yeah. It's a double method, obviously.
So you are getting that 10, like one one.
Once one I'll read from MSB.
Okay.
10100.
Okay.
That is correct. Then 111. That is also correct. Then two zeros. There are two zeros.
There are two zeros at 6th and 5th position. Okay.
After triple, yeah, two zeros, and then 11000.
Then I will have one here, one here. Okay.
11 and three zeros. Three zeros. Yeah.
So it should be this.
So initially it is 10.
No. Initial 01 is correct.
Initial I am picking
The
for the
16 bit, the
15
15 bit is zero. It's a
Yes.
15-bit value. Yeah.
So when I convert it to 16-bit, I will have 10 in the beginning. So is this number fine, right? It's what you are getting.
Yes.
This one here, and that is 16-bit. Yep. So I need to basically do the XOR operation with the 16-bit here. That is with this one. And what I will be getting here is 1. So last 16-bit I'm getting as this 11 triple 0, 11 double 0. I'll ignore the first 4 here.
Sir, I think the last two bits are 10, not 01 in the answer, whatever you wrote.
Okay, you are saying here, right? Yeah, correct. It should be 01. So what I see here, the fourth one is coming out to be correct here if I consider last 16 bits. Thanks for correcting the error here. So 11 000.
Also in the fourth option, we have the digits same, but apart from those 16. So that is obviously the answer.
Yes.
Because only those 16 will change, rest will remain same.
Yeah, in the option, yeah, the more clever this questioning should be. You should keep the first 16-bit identical, first 8-bit identical. Otherwise, there is no point. True, true. Okay, I guess we have answered this part. So let us come to this CRC interleaving part. So we have to do CRC interleaving on this particular bit sequence and provide the output bits. So CRC scrambling, we understand that base station does, it's base station's way of telling user that the DCI it meant for that particular user. What is the job of CRC interleaving here? Because in context of PDSCH chain, we are seeing that interleaving is done to remove this burst, to handle this burst error thing. That is okay, but is the goal same here for CRC interleaving, or it's something else when it comes to the PDCCH chain? So, yep.
It helps in blind decoding, and then the CRC bits which are generated from, I mean, the earlier message bits, only those are used first. Those are transmitted.
Okay, so you are saying that purpose of CRC interleaving here to help in blind decoding, and
Yeah.
how exactly it will help in blind decoding? You are
The 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 redundant bit which needs to be computed from CRC, the message bits only which I mean the message bits on which it depends, only those are transmitted first. Those are, I mean, brought first.
those are brought first, okay, and fine. So you are
And
saying it will.
then CRC bit. Yeah, correct. Yeah, yeah.
Okay, so
Then the bit, and then subsequent all the, I mean, CRC bits, and then whatever bits which on which it depends on are transmitted. In that
Okay.
way, it is
Okay, so
internally.
you are saying that interleaving is done in a very sophisticated manner. So for one
Yes.
particular CRC bit, that like when I talk about a CRC, it's done based on some polynomial. So in that way, it is a function of both polynomial and input bits, and that polynomial is going to decide that for a particular CRC bit, which are the input message bits responsible for generation of that parity bit, and interleaving is done such a way that in the interleaved output the message bits which are responsible for the generation of parity bit comes before it always for all the CRC bit, right? Is that what you are saying?
Yes. 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 Yes.
Okay, fine. uh, this part is clear to us. So next thing what I want to ask, that how it's going to help then. It's fine, I get a
Blind
interleaving.
decoding. Yeah. So CRC bitwise CRC is computed. If there is a mismatch, I mean, it stops abundance. I mean, further decoding or further checking validation.
So let's say my first CRC bit comes out to be something based on the earlier message bits that are decoded, and that is not matching, so I can stop immediately
Correct.
without
Yes. Immediately
wasting,
stop it.
okay, without
Yeah.
wasting resources on the decoding rest of the bits.
Correct.
So
True.
it's what you are
True.
referring to. Okay, okay.
Yeah.
So it's asked that something called as mother interleaver pattern. So what is that? For example, we have the figure here. So what do we mean by the mother interleaver pattern, and why is the concept of mother interleaver pattern is even arising here?
Because we can do any interleaving from this mother interleaving pattern. Means we can do any number of bits interleaving.
Okay, so whatever goes into CRC interleaver is the output of CRC scrambler, right? If I
Yeah.
talk about that chain, fine. So what is the maximum length of the output of CRC scrambling block? So
It's
you
164.
164. So in downlink, my DCI is limited to 140 bits. If I append 24 bit CRC, that makes maximum 164 bits, and that is what the output of CRC scrambling block possible maximum. So my mother interleaver pattern is sequence of length 164. So you are saying that we are calling it mother interleaver pattern because we can find the interleaved sequence for any DCI sequence length. For example, the bit sequence that is given here is of length 4, 8, 12, 16, 20. Okay, fine. I have K as 20 bit length sequence. So this is the input that goes into CRC interleaver. So can you tell me how I am supposed to find the interleaved output from here?
And we find out the intermediate value, subtract 20 from 164, find out the value.
Okay, so some number, some scalar, that is you are saying 164
Hmm.
minus
Minus 20
20. Okay, we get a number here 144.
and, and subtract this from this table given and take all the values which are greater than this 144 positive value.
Okay, so if I am calling it something as pi here,
Right.
so you are asking me to do some pi minus h thing and
Correct.
pick only the positive
You'll
indices.
get exactly you'll get, you'll get exactly 20 values over here in this array. Bigger index.
Okay, okay.
And greater than 144 in the same order.
Yeah, like, so you are saying I should subtract h from this mother interleaver pattern and only pick those elements in these indices which are greater than 144, right?
Greater than or equal to
Greater
0.
than
Greater than or
144.
equal to
Or equal to
144.
144? 144, yeah.
Okay, so which one will come first in this sequence? Like if I go via this line,
146.
146, but we have 141 here also, right?
141 is less.
Okay, so then 142, 143 here. This 144 we pick or not?
145. So it is 145. 145.
Okay, but 144 we can also pick, right? Because it needs to be equal to or greater than, and zero index is fine.
Yeah. Yes. Yes.
So this will come as 0, then comes 145, that will be 1, then 146, 2, 47, 48, 49, 50, 51. 52, 3, 4, 5, 6, 7, 8, 9.
In the lecture, it is mentioned that H is subtracted from entries of 5 such that it contains integers smaller than k in the permuted order. That means we don't have to take 144, the first one. We have to start from 145. It is written smaller than k.
Okay, it is mentioned.
H is subtracted from entries smaller than k.
Okay. Uh, uh, so H is being subtracted from the entries of the other interleaver pattern, right? And only terms which are going to remain are greater than or equal to 144, right? Is it mentioned, or it is something else?
No, it is smaller. That means the smallest value has to be 144 but not equal to.
Actually, it is written like that, but whenever Sir has written pi minus h, he has taken 128 also. So we should write.
Okay, sure.
It was because the value was 13. The n was 13, 36 there.
Okay.
The length was 36. Here the length is 20.
Yes.
Here the k is 20. So in the lecture it is 36. So for 36 he has an illustration given in the session.
Okay.
In the lecture, the value was 128, though the from the mother pattern they have taken from 129, I believe.
See, in the middle, he has written 128 also. You can see
In the middle, it is written that I agree. No,
that.
it is taken all the values starting from 129. Starting from 129, all the values are taken. Not only greater, all the values.
I guess
All the
when
positive values.
All the values, whether it is less or higher.
I guess when it's 36 in that 36 in that scenario, H would be 128. So in that case, if I
Yeah.
look at the table here, it will start from here, peak 129, 132, 134, 138, 39, 140 in the sequence, and then 128 will come somewhere in the middle. So
Yeah.
When 128, he has taken in the middle, not in the beginning.
yeah, not in the beginning. It won't take in the beginning. First of all,
Okay.
we need to subtract H from this order, and
Okay.
then we'll pick the elements. So
Okay.
in that
Sir,
case, yeah,
sir, here whatever you have written the indices, in that it will come till 19 only, right? 0 to 19. 20
yeah,
won't
yeah,
come
yeah,
because
20 won't come, correct, because we are starting from 0. So this example here which I have given is not really giving the clear picture, and this is partly because practically you won't have a bit sequence of length 20 because your CRC is itself 24 bit, so it should be above that. And in the lecture it's been covered as a 36 bit sequence, which is more appropriate, which actually covers this aspect well, because if it's 36 bits, uh, yeah, if it's 36 bits, then this indices will be something else. For example, this is coming as 1 here, then comes 4, then comes 6, then 10, 11, 12, and then 0. So in that way it's more easier to comprehend. I mean, uh, the this bit sequence will be arranged as per the index given here, where this example I am discussing as of now, it appears it will be from 0 to 19, so plain
Okay.
vanilla like sequence appear as it is. So, and it is partly because I was trying to keep a smaller sequence of length 20, but in practice it won't even appear because the CRC bits is itself 24. So the sequence length should be more than that, and this is the reason this sequence index, like according to this indexing, like interleaving pattern, the sequence will, the input and output is going to be same only, there will be any difference because the index are in the same order. But if you consider the 36-bit sequence that is being covered in the lecture, there your index interleaved output index is going to be like that, and in that case your input and output sequence are going to be different.
So that means we have to take greater than or equal to, even if the first one is 0.
uh, yeah, okay,
Okay.
okay, just 1 minute. Greater than or equal to, you are saying, in, and you just
In the example, in the lecture, the first is not 0 because we are studying of 129. But
yes, yes,
here,
yes,
if we are taking equal to, so first becomes 0 because we are starting from 144.
yes, correct,
Okay.
correct, correct, correct. In that uh, example, 128 comes later, so the 0 parts will come here as per this sequence was. But in case of our example here, since 144 is appearing first, so 0 will come at the
Okay.
first.
Got it.
Yep.
Sir, I have a doubt.
Yes.
Like, this is about downlink. Like for uplink, uh, K is like DCI length is large, right? So we can't use this mother interleaver pattern. So in that case, how do we do?
DCI length, your, okay. Uh, this question answer I don't really know. I don't know whether it will be covered in the next week, but whatever I till studied now is week 5 content only. So I don't have an idea about that. But
Like, is it like do we need to do segmentation and then perform the same thing, or um,
segmentation is of course is going to be there because you have maximum length there 1706, and polar encoder, the maximum it can handle is 1024. But even after segmentation, let's say if you have a one block 800 bits maybe, or 700, fine, then how does it happen? I need to study that. Maybe I'll be able to answer in the next session.
Do we really require interleaver there? Because this is to help receiver to decode, right? And to save the
Okay,
power.
okay, okay, yeah, forgot, correct,
So,
correct,
so,
correct.
so the base station is decoded in case of that.
uh, so
Base station is receiver. Well, yeah.
interleaving is especially for downlink scenario. Correct, correct. Thanks for reminding me, because in the uplink, you base station exactly know where your information is coming. So there is no concept of blind decoding in the sense. It's only in context of user, because user doesn't know. And we are doing the interleaving, CRC interleaving here with the sole purpose of, so that we can mitigate the power uses in the blind decoding, just to facilitate like early termination. Whether if we talk about in the uplink, base station exactly knows, because it is the one which told user to that okay, you send your information in this resource block. So in that case there is no blind decoding, so there is no need for CRC interleaver there.
okay, sir, fine.
Yeah, like thanks for pointing out these things. I completely
Because
forgot.
base station has to get all this control information received from all the users,
Yes,
which is about channel conditions mostly.
yes.
Okay. Sir, one more doubt I have. When we speak about uplink DCI, is that the DCI sent by the users to the base station, or the base station only sending during uplink you use these as a control channels like that, control variables like that?
Um, When I talk about DCI format 00 or 01, it's about the uplink grant, like the information that the base station transmit to the user regarding its uplink scheduling and all that. But um, you're talking about uplink DCI, right? So in the course it is mentioned that the maximum DCI length in uplink is 1706, and this is partly because you have to transmit the CSI information, which is some usually quite longer compared to the control information, right?
Yeah.
Yes.
And sir also mentioned like this, it will contain the CSI information which will be sent from user to the base station.
Yes.
So I got confused whether this DCI from base station to the user or user to the base station.
Yeah, since you asked the question, now I also have this confusion. Um
The channel is estimated by user only, right?
yes.
Channel knows, right? The user knows, I mean, what is the signal strength, how
Channel
much
is
is the
what
noise.
is estimated by the receiver, not particularly user or base station, I think.
No, it really depends on the distance, right? So it knows, I mean, and then what is the signal strength that is received? The user knows, right? User has to estimate channel, I mean, or base station. User, right? At user level, at user equipment level.
Sir, I think during uplink user will estimate, during downlink user will estimate, during uplink base station will estimate. But I'm not sure about this.
I think we need to stick to the syllabus of what this session is. We are
Correct.
going forward.
That is also correct. That is also
Why we
correct.
need
Yes.
to take care of
Yeah.
it now only. Sir will
Yeah.
tell whenever it is required.
Yeah. True. Agreed. True.
Actually, in the
Please stick to the
we
syllabus.
can
Yeah.
talk about our research here. What we usually do, like a base station, uh, um, user transmit pilots at the base station end, and base station usually estimate the channel of this base station user, and based on that we decide the precoding, like whatever precoder and beamformer we are going to use. That is what usually happen. And when it comes to the CSI feedback should be there, like from user end also. But okay, I'll note your question down, and I will get back to you with the answer in the next session, okay, regarding this.
Sure, sir.
So which are of following are the correct statements about polar encoding on downlink control information? Can the mother code length could be greater than 512? It's not possible, right? So this is out of option. Can the code rate of polar encoder be lower than 1 over 8?
Hmm. Yes.
Well,
No. It should be greater than one or eight.
yeah, because your mother code rate is 1 over 8, you cannot go beyond that. And third one is mother code rate length should be greater than the length of DSI. Should that happen always?
This. Okay. So obviously this has to be true.
Yeah, this of course should.
Yes.
So that third statement is only correct. Okay, this is about the frequency domain resource allocation. So we have discussed about the time domain resource allocation. When it comes to frequency domain resource allocation, what is the difference in context of time domain resource allocation? Is that some fixed length bits sequence, or that can vary?
I think that can vary.
That can vary. Okay, that is one thing. And since it's mentioned here type 0, so there must be some other type also. So what are these things? It denotes like type 1 or type 0. There are two type of frequency domain resource allocation. One is type 0 and another is type 1.
Type 0 is bitmap based, and type 1 it combines starting position into the and the resource allocation into a single value.
Okay, so type 1 is more like a continuous PRB
Continuous.
allocation.
Yes.
So you have a starting position, and from that position you continuously allocate the number of PRBs, and you get
Yes.
done with that. And what about type 0?
It is based on the bitmap we allocate, non-continuous. This question is on non-continuous.
Yeah, this question is on type 0. So let's consider a hypothetical scenario where there are few subcarriers. If I talk about from the lower end to the higher end of this 100 megahertz bandwidth, let's consider there are the channel condition is really good on the two extreme of the bandwidth, but channel condition is bad in the middle. So what kind of frequency domain and resource allocation will be helpful to you in that case, type 0 or type 1?
Will you please repeat the question?
Okay, let me just make it a bit more clear. Like, let's say like you have 100 megahertz bandwidth, right? And there are 275 PRBs or 3300 subcarriers. So I am saying that there are some subcarriers where the channel is really good, and there are some subcarriers over which the channel is really bad. And these good and bad subcarriers are like just uh, randomly placed. So what kind of frequency domain resource allocation you think is going to be helpful?
I think type 0.
Type 0. And why is that?
Because we are choosing randomly, not continuous.
Okay, so for the type 0, I have the liberty to pick uh, subcarriers in a non-continuous manner, as you said. Let's see if like first to fifth subcarrier are good, I'll pick them. Then maybe 11th to 15th, they are good, I'll pick them. But those are not available in continuous, like type 1 frequency domain allocation, right? Because in type 1, once I fixed my starting position, from that point I have to allocate continuous PRBs. So in this question, it's mentioned that since it's a bitmap based allocation, so your total number of, so okay, this is a good point. Like there are 275 PRBs, right? So is that true that we are going to have like 275 bit sequence for the frequency domain resource allocation if I choose type 0? Because when you are saying bitmap based, basically for each subcarrier you need to assign one bit, right? We are using one subcarrier, we set it to 1. We are not assigned, we set it to 0. So that way I need 275 bit sequence. Is that affordable or not? My downlink DCI maximum length is 140 bits, and frequency domain resource allocation is just one field among that. And according to type 0, I am saying I need a 275 long bit sequence for frequency domain resource allocation. Is that even possible?
Certainly
No.
not. Yeah.
So how do we handle that?
It's RBGs which are given, resource block groups.
So you have resource block groups. So what does this group stand for here?
These are group of, carriers, subcarriers.
Okay, so you are saying we have group of PRBs. So it not
Yeah.
exactly non-continuous in that sense that you can assign one by one PRB, but you can assign a group of them, maybe a group of 5 and 6. And how does it help?
It reduces the bitmap over there
It reduces the bitmap.
by that much order. By that much order.
So for like I have 275 PRBs, and earlier I was requiring 275 bit sequence. Now if I have a group of 5, I can immediately reduce it to some
Divide by 5. Yeah.
55. Okay, 55 bit sequence.
Yeah.
So the question is given that total resource block group present are 11, and these are the index set I am going to use. So what is going to be my that
None of the answers are correct.
No, answer is there. Answer is number 1, right? Whichever bits which are there, no, 2, 3, 4, 7, 9, 11. Those bits are 1. Other bits are 0.
There is
From
no
the from
triple one. 2, 3, 4 means
I
triple one.
yeah. So
Triple one is not there anywhere. So that means
acha.
all answers are incorrect.
Oh yes. Okay. Yeah.
okay, so why is incorrect you're mentioning?
I'm saying
The
2, 3, 4 means triple one. So triple one is
yes.
not there in any of the answers. So all the answers are
Hmm.
incorrect.
Sir, can you do it fast?
Yeah, sure. We have just one question left. We'll wrap it up within like 5 minutes.
So
So
with the
No,
RBG index which are given over there, the corresponding bit should be 1 in the answer. Starting from MSB. Starting from MSB or
yes.
significant bit.
So can the first answer be wrong or it's correct?
The
No, it
fourth
is
bit
wrong.
here.
2,
It is
3,
also
4
wrong.
means
Yeah.
triple one.
Yes. It's wrong.
But we cannot start from 0 here, right? We are starting from 1. When I
We can start from so the answer
You can
will
start.
be 000111.
Yeah.
so if my like resource block group are 11, so there should be 11 bits in the sequence, right?
Yes,
And
0 to 10.
my RBG index set is there is no 11, so the first one is going to be 0. Like MSB is going to be 0, right? Because this one corresponds to
Yes.
11th. Then comes 10 and 9, those are present, so there are ones.
So it is a reverse order.
It is reverse order. Yeah. MSB is on the left hand side.
Got it.
MSB is on the left hand side. So MSB corresponds to least significant index. Least index timing.
So in that way, first one comes out to be right.
So the 2, 3, 4, as he has pointed, no, the
Hmm.
3 bits should be consecutively 1, which are not there.
No, it is there now starting from the other side. So
Yeah,
it will be double zero. Yes,
yeah.
starting will be double zero. This is there.
00, 111. 00, 111 is not there.
Double zero. Why double zero? Like you are saying,
0 and corresponding to index corresponding to
Yes,
0 and 1.
0 and 1 will be 0.
but
0 and 1 will be 0.
zero is not required here, right? If we talk about, if we start from the first subcarrier sense, like if there are 11, let's say there are 11, so if I calculate from 1 to 11, the bit sequence is going to 11, right?
Yeah. Anyway, bit sequence should be of 11 length. That is no doubt.
Yeah.
The total number of RBGs are 11, so the bit should be 11.
Yes.
So whether we should start from 0 or 1, that is a question.
Hmm.
And that 0 or 1 corresponds to most significant bit or least significant bit.
Yeah. So on the left hand side, you can consider it to be like the most significant one in this side.
So left hand bit is most significant bit, no doubt, but it corresponds to least index or highest index.
It corresponds to highest index.
Okay.
It corresponds to highest.
Then the first answer is correct. Then the first answer is correct.
Okay.
But as far as the diagram drawn by the professor, no, there is 1-to-1 corresponding with respect to the least value, the most significant bit. The first bit corresponds to least index. The diagram is drawn like that.
Okay.
The arrows which he has pointed out, no, the most significant bit correspond to least value. That's what was the diagram.
Okay. Then actually what I will do, I will double check the answer here and I will update it. Okay. When I will like upload this PDF here in the folder, I will make sure the answer is correct.
Okay. Yes.
Okay. So this is the last question. It's quite easy for you. So what is the modulation scheme used for PDC? We have already discussed it.
Discussed it. Yeah, correct. Second one.
So this is the QPSK, and so we can conclude the session here.
Why not BBSK?
Because
Why not the first one?
Because that's what the standard defines. It defines that for control information, the modulation scheme is always used is QPSK. Now why not? It's a good question, because BPSK would be more robust to QPSK, that's true. But that's what the standard defines. For modulating the control information bits, the modulation scheme that is used is always QPSK.
Okay. And are there any programming exercise we are doing this particular course?
About that, I'm not really sure, man. I told earlier that I will try to hold one, but there was no instruction to me to do that. But whether I will can arrange or not, that's the issue. Okay, let me just I'll make up my mind by next week's session maybe, and I'll inform you about whether we'll have a session or not.
Okay. Maybe you can share what you are doing. You said you're working in 5G standard. You are doing some research.
Yeah, I am doing my PhD.
Okay. Okay, you plan.
Okay, sure.
I have a doubt on the previous question.
Which one? Like in this one?
Yeah, this one.
Okay.
Actually, in the lectures, some formulas are given. CRC is scrambled with 16-bit RNTI. It is written from 0 to 15. And then RNTI 0 is the most significant bit of the RNTI binary value. But in none of those formulas I see the reverse order. It is always the same order. Like it is 0 to 11, 0 to 10 for 11 bits, and then we go in the starting from 0, not in the reverse order.
Yes.
So please clarify this out also, whether it has to be reverse order or the same order.
Okay. You are asking in context of this question, right? This option.
This question or any similar question, the order has to be similar or it has to be reversed. That is doubtful.
Okay. If I talk about the RNTI,
Like we CK, there is a formula CK equal to BK for K equal to 0, 1, 2, and DCA plus 7. So in none of the formula the order is reversed.
Okay, so let me just get to the RNTI example here. So here when it's 21400 na, so our the
Here also we have not reversed the order. So here also we have reversed the order 1 to 15, 0 to 15. Here too we have to reverse the order because we have to convert it to binary decimal. The conversion will be reverse.
okay. So by the way, when you mention reverse, can you like point it out, like in context of this
No,
question?
no, sorry, it's not RNT. I'm on the same question only where our RBG index set is there.
Okay, okay, RBG
RBG,
index they are in. Okay, okay,
RBG index set.
okay. Here.
Yes, yes. So what I'm saying, the reverse order is to be done in RNTI case, not here. Here the order should remain the same. It is not reverse. That means the first we have to start with first like for 11 BWP we have to take numbers 0 to 10. 0 is not matching, so it will be 0, 1 will be 0, then 2, 3, 4 will be triple 1, 5, 6 is not there, it will become 0. So that means we have double 0, triple 1, double 0, double 1,
Okay,
one
okay,
101 and 10 double 1. This will be the answer.
okay, okay. So I'll do one thing, like I will just double check this one, and if correction is needed, I'll make the correction and then I'll upload
Good,
it.
good.
Okay.
Yeah. Because from my understanding, the order should not be reversed here because this is not RNTI.
Yes, yes, I got that. I got that. Sure. I'll just check it once and let
So
you know.
that also confirms with the diagram drawn by the in the on the PPTs.
Yes, yes.
If you can recollect the diagrams drawn, the arrows which are drawn from the bits to RBGs, that also conforms to that.
Okay,
Bits to
okay.
RPG, let me open that. So, let me open that. I can share my desktop
Yeah,
after
sure.
opening.
Please share it.
This is which lecture number?
I think towards end only. Towards end only, I think it is.
25th.
Yeah, towards end, the last lecture probably.
Okay.
Most probably.
It is
This
25th.
is lecture 2 of week 5.
Lecture 2 of week 5.
Lecture 2?
Yeah.
It's not lecture 2. Wait, is it lecture 2?
22.
That's what.
Yeah, this related to RGB, right?
Yes, yes.
Not.
Related to RGB.
You are copy pasting each and every screen. You are taking screenshot of each and
Yes,
every one.
I'm taking
Yeah, that's great. Then you can share. You can share with us.
Okay.
Please share. Or otherwise, there's a request from all of us that please share the PPTs. The PPTs which are displayed in the
This
classroom.
is not a PPT, this is the screenshot of all the.
The screenshot makes it very huge. Screenshot all those images, makes the PPTs very huge.
Yes.
It becomes difficult to share.
Yeah.
Why are not PPTs shared? Any reason? Yeah.
Oh, you are asking me.
You are asking. Yeah, yes, yes. Yeah.
Okay.
Please.
Okay. Like as you said, that's proprietary right of sir. So I
No,
cannot.
bro.
I
This is, yeah, this one. Yeah. So
This
yeah,
is type 1 and this is type 0. See,
yeah. So
the first one is mapped to the first one only, RBG 0.
correct, correct, correct,
So
correct,
the
correct.
order is not reversed. It's the same order.
Yes,
Okay, okay.
yes,
Now I get
yes.
it.
Then 1 2, it will be double 0, triple 1 in our
Like
case.
yeah, according to this figure, yeah, it should be like that
According
only.
to this figure. It should be like that.
Okay, I'll
And the
make.
indices start with 1 to 16.
1 to 6,
Indices starts with 1, right?
1, yes.
Yeah.
So I'll make the correction then.
If there is a request from all of us to share PPTs, I mean, can you pass
Uh,
on this information?
Yeah, but we don't have the everyone's contact details. We don't have. No one is having.
okay, I'll Like, have
You are there in, you are there, you are from Kanpur only, right? IT
yeah,
Kanpur,
yeah,
right?
yeah. I'm from IIT Kanpur only.
So, I mean, you meet Professor, right?
Yeah,
Professor Budhi
so
Raja.
yeah, I will
So,
then.
so there's a request. So there's a request from all of us to pass on PPTs.
Sure, sure, sure. I'll.
So those the PPTs are very very nicely prepared. It is very difficult to read all the standards and create such PPTs. Those are very nicely prepared. And if we get it, no, it's nothing like it.
Okay, I'll convey the message. Sure, sure.
Actually, I met professor in one of the webinar in seminars in Delhi. So his opinion is that we don't share the content, otherwise the people will not look at the videos. Someone asked him. Otherwise, people will look only at a PPT. No one will look at the videos. This he don't want.
But I mean, anyways, I mean, we can have screenshots then and then somebody will do it and somebody would post it, all the screenshots. So if you are doing no Lokesh sir, if you are doing it, please
For
post it.
Prashant, I send you a request on LinkedIn. You can connect with me and I will share with you on LinkedIn.
Yes, 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 yes. I'll share my email ID. We can have a I mean Google this the drive on a we can get a drive on the cloud.
Google Drive will not be possible. I will share one to one with you.
Okay, that's fine. Okay, thanks.
Okay, then I think we can conclude today's session. Let us meet us on
Yeah,
next Saturday. Thanks,
yeah,
everyone.
thanks.
Okay,
Thanks.
thank you so much.
Thank you, sir.
Thank you. Thank you.